Hi, my name is Jim Williams. I'm from Linear Technology, and I'm here today to talk about diode-induced stress in switching regulators. Modern electronic systems feature low voltages, which permits low voltage processes to build faster switching regulators, which everybody likes because the size solution goes down. There is, however, a potential problem, and that's this diode-induced stress problem I want to talk about today. In a typical boost regulator, the output voltage is nominally about one diode drop above the switch pin maximum voltage. But at extremely high speed, the diode takes some time to come on. This is graphically shown down here with the diode excursion coming up here above the nominal diode clamp voltage for some very small period of time, typically nanoseconds. And it can, in a low voltage process regulator, exceed the IC breakdown limit, which will cause failure. You've got the same problem in reverse. On a buck regulator, you'll turn on the substrate with extreme negative going excursions due to delayed turn-on time in the diode. So what are we going to do about it? We're going to have to test diodes we're going to use in our circuits for this problem. And the typical conceptual diode turn-on test is really, conceptually anyway, very simple. You put a 4 or 5 volt pulse into 5 ohms into the grounded diode, and you measure how much time it takes the diode to clamp to V diode. This looks very simple, but instrumenting it gets relatively sticky. The pulse generator has to have sub-nanosecond rise time. It has to feed a pulse current amplifier with a rise time of just a nanosecond or two and very clean transition characteristics into this same network we talked about up here. Then, because the overshoot time is so brief, again on the order of a couple of nanoseconds, you've got to have an oscilloscope with at least a gigahertz of bandwidth to capture the information you're after. Let's take a look at the pulse amplifier, which is the only piece of this thing we're going to have to build. It's basically a parallel Darlington configuration made up of RF transistors, well bypassed, emitter ballasted so they'll share current. We have to peak this thing to get the response shown over here. And the way we peak it is we just take a little bit of the rise time off the sub-nanosecond pulse input with this edge purity network in here, and we peak the f-tau of the transistors, of the RF output transistors, by varying the supply voltage up and down. These two adjustments, this adjustment, and this third adjustment here, interact, but if you play with them long enough, you'll get a 5 volt pulse into 5 ohms. That's an amp that's going to go into the diode when we install the diode. You'll get a 5 volt pulse into 5 ohms that looks like that at 2 nanoseconds per division. Very clean and crisp. Now we get a little more specific about the test fixture. This is what is by now our old friend, the pulse amplifier, driven from a sub-nanosecond. This pulse generator mentioned here, HP215, has about an 800 picosecond rise time, drives the pulse amplifier, goes into the diode under test with a 5 ohm limiting resistor, and looks at a 1 gigahertz oscilloscope to monitor the diode overshoot on turn-on. These 5 photographs are quite revealing. They're simply labeled 1, 2, 3, 4, 5, and they represent 5 commercially available diodes. In the first diode, the diode comes up and only peaks about 200 millivolts before settling into its clamp voltage. This is a Schottky, so it's clamping around 450 millivolts, but it only peaks 200 millivolts. Diode number 2 is also a commercially available Schottky diode, but it peaks almost 700 or 800 millivolts before settling. Diode number 3 peaks pretty much a volt before settling, and these are all 2 nanoseconds per division. These diodes down here are PN types, So they have a higher clamp voltage when they finally settle, but notice they clamp well above a volt. This one goes off scale. These three, actually these four, are potential causes of failure in a 6-volt switching regulator operating at a 5-volt output voltage. This would be the diode you would want. The lesson here is clear. You've got to characterize and test your diodes for use with these regulators when the output voltage of the regulator approaches the breakdown voltage of the switch pin. For additional information, please refer to Application Note 122. You can also call me direct or visit www.linear.com. Thank you for your time.